Good day and welcome to this tutorial. In this tutorial, we'll be solving a simulation problem that was sent to me by someone. Right, so this is the problem statement. So this is a case where the data for the model is actually given or is stated, and then you are asked to answer some questions. Right, you are asked to answer some questions based on the model that has been simulated. Now, when you are given something like this, the first thing you want to do is to read the problem statement properly so that you can properly understand the data that was given and know how best to use it. Right, so this is what we'll be modeling, and we'll be making use of Aspen Plus to model this particular simulation. Now, and you already know that when you want to start your simulation, the first thing you have to do is to add your components. So for example, we have the feed stream having this composition, and then these components you have from CO to isopentane. Also in the problem, we still have a few other components, right? So we'll be adding all of them to the component list. Then from what I can see, the property package is PSRK, right? So those are the first things we'll be doing. We will first add the components and the property package, right? So this is the Aspen Plus environment. We have CO. Just type the name in the component ID, name of the compound or component you want to add. So from what I see, we have CO2, then we have N2. From the problem statement below, we have like two components. We have like two components that are not they are quite rare, so we'll be using the find to look for them. We'll be making use of this to actually search for them, right? So but before I do that, I would select all the data banks and add them to the selected data banks, right? Because I don't know which category those components fall under, so I will just add everything to the selected data bank so that HiSys can search for them on the selected data banks, right? So I want to search for those components, so I've added all the data banks to the selected data bank so that HiSys can search for those components in all the data banks, right? So I will now type the name of that or those components. First one is tetraethylene. I will just type the full name, tetraethylene glycol. Tetraethylene glycol. Tetraethylene glycol dimethyl ether. Dimethyl ether. Right, so I will now click find now. So it searches from all the selected data banks, right? So this is it. Let's increase the size of this guy. Yeah, so this is the compound. So you highlight it and then you click on add selected compound, then you click add, right? So it has automatically been added to the component list. We'll do the same thing for the second one. At this point, we are done with adding the components from the problem statement. So the next is to select the fluid package, the property package. So you go to methods, you click on methods in your navigation pane, then you can use all so that all the fluid packages will appear in the drop down list. So you change your method filter to all, then you search for the fluid package you want. In this case it's PSRK, which is this. Yes, So we have, let's go back there. So we have PSRK. So when you are done with that, you can click on next, right? You click on next, then you click on next again. Yes. So now you can enter your simulation environment, right? Once you have specified the components, then and you have specified the fluid package, and then the in this case the binary coefficients have been estimated, you can now get into your simulation environment, right? So you get into your simulation environment, you click on simulation, and you are here. Now, a summary of this particular model is that a feed stream is cooled. Yes, it's cooled. Then it's sent into a flash tank, right? Then the vapor outlet of the flash tank is sent into an absorber where absorption takes place, right? So that is the summary of this particular model. So the feed stream is cooled and then it's sent into a two-phase separator. Then the vapor outlet of the two-phase separator is sent into an absorber, right? An absorber, a column where absorption takes place. So that's it. So that is what we are modeling now. So just when you are given this kind of problem, you try to understand what you are about to model, right? And then you try to read in between the lines, because some of these statements that are being made in the problem will help you specify your simulation as you are modeling, right? So the first thing we will do is to specify the feed stream, right? The feed stream is the first. So you can just get out a material stream and name it feed. So you can specify that. You can specify this feed stream. From the problem statement, we have feed stream is 60,900, 30 degrees Celsius. So let's do this. 30 degrees Celsius. Then we have 29.8 bar. 29.8 bar. Then you change your flow basis to mass so that your unit can be in kg per hour. So the flow rate was given to us in kg per hour. So that is 6,900 kg per hour, right? 6,900 kg per hour. Then you have your components. Let's check for that. CO is 8.93. The unit is mass fraction. So you change the composition unit to mass fraction first, then you specify their values. You have 8.93 E minus 5. So when you are typing a particular value that was given in raised to power 10 on the software, you use E, right? E. So 8.93 times 10 raised to power minus 5. When you are typing it into the software, you type it as 8.93 E raised to power minus 5, right? So that's how you do it. Then you have 0.498947. Okay, so I just noticed that I missed one of the components, right? After water, from the list we have, after water is isopentane. So I will just go back to the properties environment and add isopentane to the list. Let me see. Okay, I will add it somewhere here. 2-methyl let me see. Okay, it's already there. That is isopentane, 2-methylbutane. So we can continue. Let me see. 2-methylbutane. Okay, it's there. Then we can add it. We can add the composition is 1.642 times 10 raised to power minus 5. 1.642. So it will be E minus 5. Yes. So we are done with adding the composition of the feed stream, and you see the total is 1. So the feed stream is fully specified when you have a blue tick over here, right? So the next thing is to add a unit, and the first unit we'll be adding is the cooler, because the problem statement says the feed stream is cooled to 5 degrees C with 0 pressure drop across a cooler before being flashed at 0 duty and 0 pressure drop across a flash tank as well, right? So we will add a cooler. So for cooler, we go to exchangers and we select this and we place it in the simulation environment. Okay, then we need a flash tank, right? We can get that from Separator, right? So we will make use of this first one, the flash 2. Flash 2 means the flash tank has 2 outlets actually. Then you have flash 3. Flash 3 is for 3 outlets, right? Gas, light liquid, heavy liquid. That's flash 3. But flash 2 is gas and liquid, right? So you have a vapor outlet and then you have a liquid outlet. That is for flash 2, and that is what we'll be making use of in this particular model, right? So we have a vapor and liquid outlet. So you create material streams for the inlet and outlet of all the equipment on your simulation environment, your flow sheet, right? So we have, just connect them properly and name them, right? Okay, this one has not connected. Let's connect it. Yes, it's connected now. Okay, then what else? You connect your feed to the cooler. So the feed has been fully specified, right? The feed is fully specified. So the next thing is to specify the cooler. So you double click on the cooler and you can make your specifications. For the cooler, you said it's cooled to 5 degrees C, right? With 0 pressure drop, right? So now we specify the temperature as 5 degrees C because it was given. Then it says 0 pressure drop, right? So the outlet of the cooler will be the same pressure, or we have the same pressure as the feed, right? So what that means is, let's go back. So the feed is at 29.8 bar. The outlet, which is cool FD, will also be at 29.8 bar because the question said the cooler has 0 pressure drop, right? So there will be no pressure drop in the cooler. So the outlet pressure will be equal to the inlet pressure. So that is what we are specifying here, 29.8 bar, right? So as you can see, the pressure of the inlet is 29.8 bar. So the pressure of this this cooler will also be 29.8 bar as well. Then for the separator, right? So we have specified our feed and then the cooler. They are fully specified. You have the blue tick. Then the next thing is to specify this two-phase separator, right? So for example, I can click on next and then it takes me to the two-phase separator where I can specify temperature and pressure. From the problem statement, it says the feed stream is cooled to 5 degrees Celsius with pressure drop across a cooler, with 0 pressure drop across a cooler. before being flashed at 0 duty and 0 pressure drop across a flash tank, right? So here we are specifying duty, so we can change this flash type to duty, right? So duty is 0 as well, right? Duty is 0. Then pressure will still be 29.8 bar. 29.8 bar, right? Because the question said 0 pressure drop for the flash tank, right? It says 0 duty and 0 pressure drop, right? So the pressure of the inlet will still be the same as the pressure of the outlet, right? So we have that taken care of. So now this is fully specified. You can run your process. Right, so the process has been run. You can even check the stream results from, this is stream results from the two-phase separator, right? But we'll be checking the results at the end of the simulation. Now, the next thing is to simulate the absorption process. For that, the vapor outlet of the flash tank is absorbed through a rad frac column in a solvent which has these properties and then the composition. So the next thing to do is to create a material stream for this particular solvent, right? Both the solvent and the vapor outlet of the flash tank will be sent into the rad frac column, which is an absorber actually. So we create a material stream for that particular for the solvent. So I will just name it SV, right? Then we will fully specify the solvent. You have, what do you have for solvent? You have 600,000 kg per hour, 29.8 bar, 10 degrees Celsius, 29.8 bar. Then you have your mass, you are changing to mass, your flow rate. Then you have 600,000, right? 600,000. Is this right? Yes, that is 600,000. 600,000. Then you have your composition. You have these two guys. I think it should be mass frac. Yeah, mass frac. Let me see. Yes, so we are using mass frac. You have 0.49 for each, and then 0.02 for water, 0.49, then 0.02 for water. Right, so this is fully specified. Yes. Okay, so this is not water. Let's change it. So it is 0.02 water, 0.02 water, 0.02 water. Right, so this is correct now. So we can continue with the model. So we click on run, and then we can add our absorber, which is a rad frac column. So we go back to the main flow sheet to specify the column. So we go to columns, and then in columns you have DSTW, DSTL, rad frac, extract, a lot of them. So we are making use of the rad frac. Now what you do is you click on the drop down, and then you choose the exact column you are looking for. In this case, we are going to use the absorber column. So we choose absorber 1. There are a lot of columns here depending on what you want to simulate, right? Depending on what you want to simulate. But in this case, we are simulating absorption, right? Gas absorption. So we just use this. you click on it and you bring it and drop it here in your simulation environment. Then you can create outlet streams for it, right? You can create outlet streams for it. So this is let me just name it this. Then okay, then we can create the bottom stream as well, right? So we have this. So we have created the outlet streams for this particular column. Then we can connect the inlets as well. So you double click on this guy, you double click on it and you connect it to the inlet of that absorber, right? Then the next thing to do is to specify the absorber itself. The inlets have already been specified, both the vapor outlets and then the solvents, they are already specified. So what we need to do now is to specify the absorber itself. So you can click on next if you want. It takes you into the absorber directly, or you can double click on the absorber itself, right? So now here we are going to be making use of the information given in the problem statement. Now we have that the absorber has 10 stages and it performs equilibrium calculation, right? So you have calculation type is equilibrium, so we don't need to change it. Number of stages is 10. Number of stages is 10, right? Then what else do we have as information there? It says the solvent is poured above stage 1. Then the vapor is fed on stage 10. The stage 1 is maintained at atmospheric pressure. Then PSRK property method may be used, right? So let's go back and see what we have here. They are asking us for condenser type, reboiler type, right? So now I will click none for condenser and reboiler type. My reason for doing that is because there is no information about the condenser or the reboiler in that particular problem statement, right? So I'm going to click none for both of them. Yes. Then what else do we have there? They mentioned something about the feed stage, right? The feed stage. Let's go to streams. Let me see. Yes. So we are specifying where these two feed streams will be entering from the problem statement. You have that the solvent is poured above stage 1, right? So solvent is SV, so it is poured above stage 1, right? So this guy, convention is above stage, then you now specify 1 here. So this guy SV is poured above stage 1. SV is poured above stage 1. Then VAP is poured on stage 10, I think. Yes, it's fed on stage 10. So you change the convention to on stage. For VAP, it's on stage and it's stage 10, right? Stage 10. So this is stage 10, and that's it for that. Then pressure, for pressure, we have the stage 1 pressure to be atmospheric pressure from the problem statement. You have the solvent is okay. Yes. Then you have the stage 1 is maintained at atmospheric pressure. As far as I know, atmospheric pressure is stage 1. Top stage condenser pressure, stage 1, right? Pressure. So you have stage 1 to be at 1 atm, atmospheric pressure 1 atm, right? So we have fully specified this absorber. Yes, this absorber, we have fully specified it. Like I told you, the condenser and reboiler type is none because there was no information given about it, right? And normally absorbers do not have condenser or reboiler, right? I think they do not, right? So we have specified everything that needs to be specified from the problem statement. So the next thing is to run the simulation. So you just click on run. You click on run, and then the calculations will be done by the software. Then if you want to check the results, you go to the navigation pane, and then you go to the drop down. You see result summary. You click on streams, and then it gives you the result of all the streams in your model, right? So you can adjust your screen. You adjust it so that you can have more space to view the results properly, right? So these are the results for this particular model, right, from beginning to end. So you see your feed stream is there, all the streams that are involved in the process are here, and their process conditions, then the composition of the components in those streams, they are all here, right? So you can view them from the results summary section of the navigation pane. So this is what we'll most likely be using to answer the questions that are being asked, right? Questions that are being asked, right? Another way to view it is to view it from each of the streams. You can also view from each of the individual streams, or you can view from the equipment itself, right? If you don't want to make use of the result summary, right? So because it contains a lot. So let's go to the question. So the first one says the heat duty of the cooler. The heat duty of the cooler. Let's go to the cooler itself, right? So we have the cooler. Let me see. So this is the cooler environment. You can get there by double clicking on the cooler in the flow sheet. Then to check the heat duty or the properties of the cooler, you can just go to results, right? Results will give you some detail about that particular equipment, right? So this is the heat duty here, right? But the question said in kilowatt, so you can go to the drop down and change the units to kilowatt, right? So this is the heat duty of the cooler. The heat duty of the cooler is minus 1490.06 kilowatts, right? So that is for the first question. Then the second one says the vapor fraction in the flash tank. The vapor fraction in the flash tank. Okay, let's go to the flash tank. The flash tank is what? Flash tank is B2. Okay, so this is B2 already in the tabs. So in B2, you go to you still go to results, right? Right. So you have your vapor fraction. Let's confirm which one they are looking for. The molar vapor fraction, the first one, vapor fraction in mole, that is 0.672439, right? So that is the answer for that one, 0.672439. Then the next one, let me see, the boil up ratio in the bottom stage of the reboiler. So you just go to the reboiler as well. Okay, the reboiler is the reboiler should be found in the absorber, right? Should be in the absorber. So you go to the absorber and then you check the you still check the results of the absorber, right? So this is the results part of the absorber, and they're asking for the boil up ratio. The boil up ratio in the bottom stage. Boil up ratio. So this is the condenser. These are the condenser details, and then these are the reboiler details. So it's asking for the boil up ratio. From what I'm seeing here, I have boil up ratio is 0.935555. So that is the answer to that one, 0.935555. Then you have, that is for number 6. Then you have the mass flow rate of hydrogen through the liquid outlet of the ash tank. I think it should be flash tank, right? Flash tank, not ash tank. So the liquid outlet of the flash tank, the mass flow rate of hydrogen, right? So you can check that using this results summary, the mass flow rate of hydrogen. So we go back there to figure out. Now this is the liquid outlet of the flash tank. So we go to this stream and look for the mass flow rate of hydrogen, right? So we have leak here. This is leak, right? This is it. So we scroll down, right? This is it, leak. Now the mass flow rate of hydrogen. So we open the mass flows for leak and then we trace that of hydrogen. This is hydrogen here, so you can use that to trace with your eyes. So the mass flow rate is from what I'm seeing is 0.947198 for hydrogen, right, in the liquid outlet of the flash tank, right? So that's the answer, 0.947198. 0.947198. Yes, that's it. So that is for this one. The temperature of the lean gas outlet from the absorber, right? I will assume that this you are asking is the temperature of the vapor outlet of the absorber, right? The temperature of the vapor outlet of the absorber. That can also be gotten from here. The vapor outlet of the absorber is this one, the top, right? So we will use this to trace. So we are going back to the stream results summary, and then where do we have it? Okay, we have it here. This is it. This is it right here, right? So the temperature is 12.2066, right? 12.2066 degrees Celsius. 12.2066 degrees Celsius. That is the temperature of the vapor outlet of the absorber, right? Then what else do we have there? We have the molar flow rate of the rich liquid outlet from the absorber, the molar flow rate, right? The molar flow rate, let's check that. So for that we have this guy, rich SV, as the liquid outlet. So we are going to be checking the molar flow rate of this, right? Still from the streams results. So that is this guy here, right? This one, this particular column, rich SV. So we are looking for the molar flow rates. Okay, let me see. This is okay, let's scroll down a little. Okay, that is it. So the molar flow rate for rich SV is this, right? So this is mole flow, right, in kilomole per hour. So you have rich SV as 3111.86 kilomole per hour, right? So this is the molar flow rate, right? Molar flow rate for the liquid outlet of the absorber. Yes, that's it for number 9. Then for number 10, it says the molar flow rate of the isopentane in the rich gas inlet to the absorber, right? The inlet to the absorber is the vapor outlet of the flash tank, right? Do you agree with me? Do you? I guess you do. So we are going back there. Like I said, the vapor outlet is the inlet to the absorber. So this is where we'll be answering that question from. So we still go back to the result summary and we have vape. This is it right here. Sorry. Yes. So this is the gas inlet of the absorber, like the question said. The inlet to the absorber is vape, and then we are looking for what? We are looking for the molar flow rate of isopentane, right? The molar flow rate of isopentane. So we go to, yes, mole flows, right? So we open mole flows and then we trace isopentane. Isopentane is 2-methylbutane, right? That is isopentane. In kilomole per hour, we have 0.0137747, right? That is the answer for this particular question. The molar flow rate of isopentane. The molar flow rate of isopentane, yeah. That's it. The molar flow rate of isopentane. So you have 0.137747. Yeah, that's the answer. That's your answer. There you go. So that's the last question from here. And with that, we have come to the end of this particular tutorial. So this tutorial just shows you how to solve this particular problem. So like I told you, the most important thing is to understand the problem statement, right? So whenever you are given a problem, you try to read it carefully to be able to draw knowledge that you would use to simulate and properly interpret the data given, right? So you try to understand it in order to properly understand what you are giving, the data you are giving, and then what you are supposed to find, right? The questions, right? So you have to understand properly what you are giving and then what you are being asked to look for, right? So that is the key to simulating this kind of processes. I hope you have gained some knowledge from this tutorial. If you have questions on this particular video tutorial, let me know in the comment section. Like this video, share with your friends, subscribe to the channel for more videos on process simulation. Thank you for joining me. Hope to see you next time. Do have a good day.